So, can I start? Okay, today we will speak about a really simple topic, which are decision trees and random forests. The algorithms are simple, the interpretation are not so clear. So uh, it is different from linear regressions because linear regressions are quite clear mathematically, but they are quite rigid, and these decision trees and random forests are much more general, but they are difficult to interpret, and we will see why. Uh, so first, let me start with a usual classification of the data science algorithms, which are like supervised learning and unsupervised learning. So the supervised learning algorithm basically start from a set of observations, say x1, 1, xd 1, and y1. Let's say that we observe m of these vectors. So we observe m of these vectors, and we think that these vectors are come from independent copies, independent copies of a random variable x1, xd, y. For instance, we can, I don't know, we are waiting, we are, I don't know, we are measuring x1, for instance. D can be equal to 1, x can be the weight, and y can be the height of a person. And we measure various persons, various people, or some linguistic features like X can be the fact if a person determine the person is bilingual or not, and Y, I don't know, the ability, the reading score in some test. Uh, yeah. Uh, so in the supervised learning, we have some observations, and we want to predict. We observe a new data. We observe, I don't know, x1, xd again, but not y. And we want to predict y using the previous, of course, using x1, xd, xd, but also the previous observation. And the prototypical example is the linear of this kind of algorithm are the linear regression, in which y is equal to beta 0 più beta plus beta 1 x1 plus. So let me state in this way. The typical example is the linear regression, are the regressions in which the model is the following. Plus beta d xd plus some noise, which is assumed to be Gaussian and independent for each observation. Then the learning procedure is the one that with which the one with which we estimate these parameters beta zero. Beta i's. In this case, in the case of linear regression, was the ordinary least square method. Or for instance, the logistic regression, because we will do a similar algorithm today. So not a similar algorithm, a different algorithm which does the same thing more or less. Linear regression was like estimating the probability y was categorical with two levels, 0 and 1, and the probability that y is equal to 1, we took it as sigma, the sigmoid function applied to the exponential of minus beta 0 minus beta 0 minus beta 1 x1 minus etc minus beta d xd. So this was another model, and I didn't tell you because I didn't have the time, but the learning procedure with which we decide beta 0 and beta 1, beta d, sorry, there are d of them, is the maximum likelihood. This is just a random name because I didn't tell you in what thing it consists. Okay, so this is an example of supervised learning, and there are also unsupervised learning algorithms that we have seen. So the unsupervised learning algorithms that we have seen are the dimensionality reduction, we have seen the PCA, principal component analysis, and we have seen the naive k-means and hierarchical clustering. The first one is the dimensionality reduction algorithm. And the second one is simply clustering algorithm. This algorithm look for a pattern in the data without any hint. But the results have to be interpreted. Uh, Today we will see decision trees. Let's start with decision trees. So a decision tree is an object that will allow to define an algorithm to predict y from x1 xd. So okay, let me give you uh, an example. No, or maybe yes. Let me define what is a decision tree, even if it is really abstract. So it is a tree. What is a tree? It's a set of nodes and edges between nodes. Uh, where the nodes are questions. We will use yes, no answers. Um, so it's simply this, simplifying a little bit is simply this. So let me give you an example. Um, and I need to draw something because it's impossible. Okay. Uh, so for instance, we take a point x1, x2, inner 2, and we take the following decision tree. So if x1, the first node is this question. I mean, is this true or not? For instance, I mean, this can be true or not. If it is true, yes, of course, I was forgetting. Uh, so mm, it is not only I mean, on the leaves we have a decision. So it will now I will make clear what it is because, for instance, if the answer to this question is no, we can decide that y is equal to 1, let's say. If it is yes, maybe we ask another question, like, is x1 bigger than 0? And if it is bigger than 0, maybe we choose y equal to 0. If not, maybe we ask another question, like, ex1 is bigger, I don't know, is smaller than x2, and then we can choose y equal to 2 or y equal to 1, for instance. Now, I give you like a number, like 1/2 minus 1/2 0. Are you able to determine the value of y? According to this decision tree? The question is not clear. Uh, so in this tree, you have some questions, like this one, and I give you a point, this p, in which you have to see if, I mean, this p will answer to these questions either yes or no. Like, is it the first coordinate squared plus the second coordinate smaller than 1? And yes, so it will go here. Then we check this one, it is a no, it will go here. Then it is e to the power minus 1/2 is smaller than 0. Well, no, this is a no, so it will go here, and because this quantity is positive, so it can, and it will go here, and we will choose y equal to 1. So given this tree, it's easy to see what's the value of y. So let me so given a decision tree, where in the leaves is it clear how it works, the decision tree? If not, it's better to stop. I mean, not how I built it, but how, given the point, I can give you the y. So only that, because I built it completely randomly. So maybe let me draw a picture because it's better. So we have this, the first condition is x squared, x1 squared plus x2 squared is less than 1. Which are the points that satisfy this condition? The ones which are inside the circle. Because this is the equation, the circle, I mean the circumference. So if a point is here, it will satisfy let me check. Okay, if it doesn't satisfy it, we are outside. So let me do better thing. This region here in red is x1 squared plus x2 squared greater than 1. And here, if this happens, we are here. And we finish, we have no more questions, and we have a value for y. Okay, what is y? Let's say that this decision tree given an x1, x2 will give you back a value for y. Now, here is totally general. In our case, we want to predict. Okay, we want to give a supervised learning algorithm. So we have some x1, xd that we observe, and we have another variable y which we don't know, and we want to predict it. And a way to do that, which is totally different from linear regression, is I mean, I can give you whatever machinery to predict y from x1, xd. This decision tree is one of it. So on the leaves, there is a decision for y. So now it's totally general. It's simply, now I'm defining a function where I take in input two numbers and I give you as output one value of y. And this function, for instance, here, takes the value y equal to 1 because, I mean, no, I'm not asking, I will explain, later will be clear why we take this kind of, how to build this kind of trees and why. But now, simply algorithmically, I give you a value of x1, x2, and I give you back a y. It's a function. So like here, that if you are here, if the point is here, gives you y equal to. Now, if the point is inside the circle, we still have another question. So if the point is here, we have the question whether x1 is greater than 0 or smaller than 0. So we divide again this into parts. This one, which is x1 greater than 0. And let's see what happens in x1 greater than 0. Well, in x1 greater than 0, we have y equal to 0. This is a leaf. I mean, a leaf is the ending part of the tree. Because also in real trees. So here y is equal to 0. What happens if x1 is smaller than 0? Let's see. We have this condition. This condition can be written as e to the power x1 smaller than x2. I mean, is exactly that condition, which is something like this. Here we have that x1, x2 is smaller than e to the power x1, and here we have that x2 is greater than e to the power x1. So what happens if x1, if e to the power x1 is smaller than x2, that y is equal to 2. So here y is equal to 2, and in the other case, y is equal to 1. So at the end of the day, we have decided the following. Something like this, that here the prediction for y is equal to 0. Here the prediction of y is equal to 2, and here y is equal to 1 in the rest of the part. So this is simply a function that associates to x2, x1, x2, y. And this y, so it is a y of x1, x2. Is it more clear now? So, I mean, it's simply, I give you an x1, x2, you can find me following this diagram, the value of y, because you will end up in a leaf. Yes, this is an example of decision tree. I've started by saying what is a decision tree. So this is an example decision tree, and we will consider more or less this even simpler decision trees. So general definition is really not needed, this kind of stuff. Now we come back here, and what is our goal? It is to give a supervised learning algorithm that uses decision trees. So what's the difference? Why we would like to do this? Why the linear regression is not sufficient? Well, comparison the comparison can be already done. Well, first of all, the linear regression was this kind of model here, or also let's take yes, let's take this the usual linear regression. Well, this is the model, and you see it has much more information. than simply predicting y using x1, xd. Y in terms of x1, xd. It gives you a very simple model, an effective model that relates y and x1, xd. You can this coefficient have an interpretation. The coefficients have an interpretation. It gives you in practice it gives you a model, an interpretable model of how y depends on x1 and xd. However, if we are only interested, it is on the contrary. On the other hand, it is quite rigid. It's linear. And if we are only interested in the prediction, it is better to we can use other models. So let's see an example of the decision tree. The decision tree will give you a much more complicated function. Will give you y is equal to the leaves to which leaf value of y in the leaf of the decision tree corresponding to x1, xd. So do you see why? I mean, I give you a vector, you go through the decision tree, you arrive to the leaf, and you choose y. So it's a much more complicated function. Instead, that one was linear. So if you plot it, it's a plane. Instead, this one, you have to make this geometric stuff to plot it. The one we did here. So it's much more complicated. Or at least it will become much more complicated. So let's start with an example. And the typical example is y is y is categorical with 0, 1 levels. And let's try to find a decision tree, a good decision tree for the following data. This one, I will plot it. So we will plot this data x1, x2, y. Y is a categorical variable, so this will be the point. And if we plot an x means like y equal to 0, and a dot means y equal to 1. Okay, since this can be either 0 or 1. So like this point here will be, for instance, 3, 1, will be uh, 1, 3, and which value here? So for instance, or this one, which yeah, there is a 3, a 2, and which value should I put here? Yes, exactly, because uh, this is it's a way of encoding it. I mean, y equal to 0 instead of it's a categorical variable. It can be a color, so it does not need another axis. Do you do you see it? So like here it will be a 0, and here it will be a 1. And there are not like 0 0.5 that I can put in between. There are only zeros and 1. So instead of, I remove this variable here and I encode it in another way. Maybe it is better to, instead of using this, you use colors because it's like, so the one now is green. So, and the 0 is red. So this is 130 and this is 321. So let's say that we want to predict the color of the new point, not the y. Let's see, y is a color. It's not a number. Uh, do you see why? I don't know, like why can be like the fact that the guy is bilingual or not. And this can be like the age in which he learned the new language, no, the age in which he started the education, and the other one can be like uh, how many siblings does he have. So instead of plotting is bilingual, true, yes or not, you plot it, you put uh, you put it, you plot it blue, red if they are bilingual, or green if they are not bilingual. So it's not, when you have a factor, it's not really a number, it's a grouping variable, so it can be a color. So let's assume that we have this data. Mm, So can we think about a good decision tree to, I mean, how can we decide uh, the color? of this point, like a point here. Probably green, yes, because it's in the middle of a lot of greens, but we want to check conditions. So we want to make this decision tree. So let's start like what do we check before? Like, I don't know if it is here, why it would be also green.
Which axis is X1?
Ah, sorry, this is x1, this is x2.
So first we check if X1 is greater than 2.
Yes, that's a good way to start. So this is the first node, and if it is greater than 3, what do we do?
This then
Exactly, then we
one
green. And if not, so we have taken this part is now chosen, is green.
then we check if X2 is greater.
Yes. And
Yes. Oh,
yes, if it is greater than 2, maybe we are here. If it is greater than 2. Here it is x smaller than 2. So I would say red. Do you agree that, I mean,
yes.
we are here? I would put, if the point is here, I would say, I would color it as red. If yes, maybe we can do another division, which is, do you, I mean, we are here now, this part of the area, because we checked that here we took a no, here a yes. So do you have in mind another division? We let's say that this is
So
1/2, let's say.
if X2 is greater than 2 and X1 is greater than 1.
Yes, I mean, I simply add here an index 1 greater than 1.5.
Yeah.
Then I choose, if this is true, I choose the green one. If not, the red one. So do you, is it clear this part? I mean, not how, so if I give you, I don't know, this point, a point, can you tell me using this tree which color I mean, I give you a point, uh, is it clear? If not, what is not clear? So now we have decided by looking at this by quite by eye how to write this decision tree, but Now, if I give you a point, can you locate it and give a color to it?
The tree, this one, the black one is going to be, or, yeah, it will be green.
Yes, the black point, yes, because we stop immediately. X1 is greater than 3, and we stop here at the yes, and it will be green. A point here, for instance, sorry, this will be much longer because we check first the first condition, but here it is like 2.5, 2.5, let's say. So x1 is smaller than 3, so we go here. But x2 is 2.5, which is greater than 2, so yes, we go here. Now x1 is again greater than 1.5, so we color it as green. So do you agree that our previsions will be something like this? Mm, we will have a 3, here a 2, here 1.5. So here y is equal to red, and here green. Is it, I mean, uh, are you are you following, Xenia? If not, tell me because I. Okay. Okay. Then we go on, and we want to build an algorithm that give an algorithm that builds these decision trees because we did it by eye. So okay. That builds this decision tree. So we have to fix some. I mean, what do we have to choose? There are many ways to build a decision tree because I mean we can ask basically whatever. So the first thing to do is like the model, like uh, which questions we want to ask. To the data. Then we have to choose like how to fit the data. How to choose the questions to ask. Because, okay, we have this set of questions, but we have to choose one intelligent. I mean, in this case, in the example, we are asking like to separate points with horizontal or vertical lines. If we choose like the horizontal line here is not a smart choice. So we have to have a way of saying that of doing smart choices. And then we have to give to the algorithm a stopping rule, because otherwise we will finish with clusters of 1 point, and not so, I mean, it's wrong. So the questions we ask are as the ones we have chosen. So are of the so are like, is xi greater than a certain constant c? I mean, so here I'm describing a particular model, which is CRAN, I guess. Well, I don't remember precisely the name, but there are other ways of defining a decision tree, but this one is the one which is more used. So these are the questions we want to ask. Then, how do we ask it? I mean, which one? Okay, note that I don't know. There are endpoints, so we can separate these endpoints in each direction. So there are like n times d possible choices of questions, because and there are endpoints, and we can separate them in the directions. So that there are n times the possible questions. So how to choose the question? Well, we want the clusters. We want to separate the points in such a way that they are homogeneous. They are as homogeneous as possible. Well, then we have to define a function, which is the impurity function. We have to define a function that tells us how impure is a set of points. So there are basically two interesting choices, which are like the Gini impurity function or the entropy counting. So the Gini impurity function, well, it's let me like draw something. It's quite easy to be understood, because I don't know. We want to see, like, have this set of points. we want to see how much are they impure. Impure. According to Gini, well, we draw twice, we draw randomly twice 2 points, and like the probability that two randomly extracted points are different is the Gini impurity function. I mean, can you tell me what is in this case this G of this G function of these points? You need to do some computations, but it's not so. I mean, it's not immediate. Ah, well, I would do like, okay, I would divide like the first extraction gives me red. So what has to be the second extraction to give me two different results? Not red. So it is like, if in the first extraction extract a red ball, this is the probability that in the first extraction extract red. In the second, I have to extract a blue or a green ball, so not red. Then, if in the first one extract a green ball, I should extract a red or a blue ball. Or if extract a blue ball in the first extraction, then I have to extract not blue. So this is the probability of if extract two random points, they differ in this event. So in general, the Gini function is defined as GP1 let's say that there are k species. So it is like 1 minus. Ah, yes, of course, I'm doing this now for, let's say, k, so y is a factor with k levels. Then we will do it also for numerical variables. It is an easy extension. But now there are only k colors. So, and the Gini function is the sum provided across the factors of pi times 1 minus pi. Where pi is equal to the number of elements of color I divided by the total number of elements. So this is the Gini implicity function. So the algorithm, what does it do? The algorithm takes like the following set of data. Takes all the possible lines that separate, sorry, vertical or horizontal lines that separate the points. Then what does it do? It computes the Gini. Let's say we choose this line. It computes the Gini of the right set of points, the Gini of the left set of points. Okay, we should somewhat sum them, but we should also weight the number of elements they have, because otherwise, if there is only one point, I can divide it. It will have Gini impurity 0. But I mean, we really want to avoid 0 really small clusters. So what do? Is we minimize this cost. The cost is the number of elements on the left times the Gini impurity on the left plus the number of elements in the right times the Gini impurity of the right. So this one is the cost. And now I mean, do you understand why I'm weighting it with the number of elements? Hmm? I put some weight to the Gini impurity function. I don't simply consider the sum, but I multiply by the number of elements on the right. Because that, so there could be a situation where on the right there is a lot of different dots, but on the right there's only 2 different dots. So the now, yes. Well, no, I mean the Gini function is defined on each group. but we don't, since if a group is too small, we want to avoid the small groups, um, because otherwise there can be, yes, the possibility in which there is only one or two elements in one group and the other one, it may be very impure, but maybe it's the best choice, that one. And but here now, mm, um, but in that case, if like a group has a really big number and a big gene impurity, it will be very bad to choose that line. So here we want to choose, like, if a group has a, if the both groups have the same Gini number, it will be better to take them more or less of the same size. Uh, I mean, it is more like, I mean, this is more like an analysis of this, why taking this cost. But let me say simply that is to avoid situations like this one, like have two green points here, then a lot of mix here, a big cluster. And a lot of other points. So like the best choice would be that one, and maybe you don't want to take small clusters. And maybe this one is better. Well, so this is the gene impurity function. And okay, so let me state. So okay, so this was only the definition of gene impurity function, and the entropy function is actually defined. I mean, I won't enter in details with this function that is defined in this way. It's equal to the sum from I that goes from 1 to k minus the logarithm pi, the logarithm of pi. And uh, so this function has the advantage, like there are some differences with the gene impurity function, but I mean at this level it's not really it's not really important. So you can choose the best your preferred utility functions. So once we choose our favorite impurity function, let's say, let's call it EF, the cost of dividing the data into groups is the following. Into groups, let's say one is the group xi bigger than c, and 2 is the group given by xi smaller than c. the cost is equal to the number of elements in one times the impurity function of one plus the number of elements in two times the impurity function of two. And so is it clear what is this? I mean, it's a function. I'd call it cost, but and among all the caps, we choose I don't know, we choose I and C such that the cost is minimal. So this is how to decide which question to ask. So like for the linear regression was the ordinary least square method that allowed you to choose beta zero. Here we choose a node according to this rule, a node of the decision tree. Now we have to choose when to stop branching this tree. So when we will stop asking questions and giving to y a value. Well, this can be done in many different ways. Also, like we can fix a minimal predetermined minimal amount of points a group must have. Or we can fix the depth of the tree. So we can fix the number of questions we can ask to a point. But actually, the coolest is the following, which is like we do a statistical test to see like the chi-square test in this case, the chi-squared test to see whether y statistically differs in the two groups. If yes, we continue. If no, we stop. So, for instance, this is a little bit complicated, so let me draw a picture. So, like, what was the chi-square test? So let's say we have this data. No, we have divided everything. We are in this set, and y can be either green or red. So let's say that the best cut is this one. So we have here y in group 1. This is the group 1 and this is the group 2. Is y in the group so we can build the usual table, so we can see we can put here the group, here the value of y, y can be either red or green, and the group can be 1 or 2. And here we have 1, 3. We have in group 1, we have 1 red and 3 greens. In group 2, we have 3 reds and 1 green. And we have also the optim, and if you recall the chi-square test, the chi-square test was like saying if the group was significant in predicting y. In this case, there are very few. It may look that yes, but there is a very little very few points. So I would say that I mean it would look like in 2 it's more likely to be red, but in 1 it's more likely to be green. But the points are really little, and these are really few. I mean, so and this was done mathematically rigorously by a chi-square test, if you recall from a long time ago. We had to define like the best table if the hypothesis is true, which was like I don't know, the best table is the one, is this one, 2, 2, 2, 2. If they were all, I mean, but and we have to compute the distance of this table from this other table. But I mean, it is a test that tells you if y depends on the group. So was a lot time ago, so I mean it's normal if you don't remember it. So exactly that is a test that tells you whether y differs in the two groups. If it differs, we continue because yes, and if not, well, it doesn't really make sense to continue dividing. And okay, and this defines the algorithm. So uh, R, there is this function C3 that we will see from the party package. That uses this method for stopping it. So it does a chi-square test. That's it. Okay, in the next hour we will discuss about random forests, which I mean, a forest is a set of trees. So it's I don't know if you have seen this algorithm, but I mean there will be a lot of decision trees involved in it, and it will be very pretty much not interpretable the result, but and we will see some code. Okay, so let's do one break. 10 minutes. Okay, let's start again. So with random forest, so maybe let's do a little bit of code before going to random forest, which is more it's funnier. So let's take the data set that I collected by an ex-bachelor student. Name is I don't remember. I've written here. It's Sveshnikova. I don't know the name, unfortunately. And let's see which kind of data is. But it's quite slow, as usual in this hour. Why it doesn't work, I don't know. Well, I read it from here better. Okay. No, let me see. Yes, there is this data set of words which in some cases can have an elision. And so the words were like to riot, I don't remember Vesci. Okay, let me look in Google Translate. Where to riot, no, Vesci. Okay. Well, I don't remember. There is a word which can either have an elision or not. There are some words, many words, and they are classified if the elision has been used or not. Then which word is, then to which group uh, they are. Which group they are from, and the groups are like if the word is in the group one is like if the word is in infinitive. The group two like was if the word is in first person present. And the group three, I don't remember actually. I will pass you like a better file where you can find all this informations. And the position is like is logically strong or logically weak in the sense that if it is, I guess, the important part of the phrase or a part which is not the most important part of the phrase, but you know better this stuff than I do. What we want to do here is to predict if there will be an elision using these other three columns using a decision tree. So first of all, unfortunately, I have to pass this data since the C3 function admits. I don't know if always had that, but now it admits only factor variables, and these the columns are character columns. We should transform them as factors. If one is good with R, should do something like this. Phono mutate across all columns. And we use the function as factor. This should constrain as a factor every column, but I'm not good at it and it gives me an error. So, and I had no time to think about an alternative. So I will do manually for each column, which is not really the smartest choice. So Phono violation is equal to Phono violation, and we put an as factor. No, let's, for instance, see how it has changed. Okay, now the first column is a factor, and I have to take some time to do it for every column. So the group column, for the word column, and for the strong column. No, sorry, for the position. So now they are all factors. And we can use this function C3, which is from the party package. We pass it the data, which is Phono. And we want to predict, as usual, deletion column using all the variables, groups, group, word, and position. Okay, and we save it into a variable. My tree. Now, these kind of objects are much more understand if we plot them. So you see the syntax is really easy, and all that algorithm that we introduced in the previous lecture is 2 lines of code. And this is the decision tree. First thing we do is like we take a data, so like the group to which the word, the group to which it belongs, and the position, this, if it is in a strong or logically weak position. And first we distinguish the group. So this is the first division. And the p-value of the statistical test is less than 0.001. So it really, deletion really differs if we do between these variables in the third and the first and the second group. Then we decide in the third group, we again divide the data according to the position. While in the first and second groups, we divide again first and second group. So in the first group, there is really always no elision. In the second group, again, most of the times, no, sorry, there is always, there is almost always elision. And in the second group, uh, or again, a little bit more of no elision is in this when the position is strong, we are on the third group. So, like strong position, of course, can avoid deletion because I don't know, maybe you want to emphasize the word, so you don't omit anything. Um, well, this is the decision tree, and we can like predict a function, like predict. We can use also the function predict uh, to predict if whether there will be elision or not. So let's say we take this word here. So first we have to, the predict function takes my tree as an input, and then a data frame with the same variables, group, word, position. So we have to define a data frame. So let's say that the first we take from the first group and the levels are first, second, and third. Then have to take, so this was the, so yes, this was the group variable. Then we take the word will be this error, no, and the levels are the levels of the word, the variable word, and the last thing we take, let's take it in the weak position. And the levels are again the levels of phono position. So let me see if everything is correct. Mm, So maybe it's level. So as factor, it does work. Sorry, but I have to give them a factor with the same levels, otherwise it will not work. Or maybe factor, not as factor. Yes, you're right. Okay, then factor. Okay, this gives me my data frame, and I can predict using my tree and my data frame. Okay, let me save it into that. Uh, so it predicts yes that there will be a lesion simply because we are. Let me plot again the. Simply because we are feeding some word from the first order, from the first group in weak position. So like it sufficient to be on the first group in order to predict an elision, that there will be elision. So what do you think it will happen if like we change the word instead of this word we use BSG? I don't remember which word was, so unfortunately, according to this decision tree. Like the variables cannot change really too much. The group can be the second, the first, the third. The word can be, I don't know how many levels are there, but let me check. So levels, phono, word. There are six words. So and three groups and two positions. So not many variables. And so if I change the word, does it change where I will my prediction? Sorry?
Just the prediction on the group.
Yes, yes, yes. Do you remember that when we were talking about numerical, we were trying to use numerical variables to predict y it was easy to each to each x1, x2, we could give to y an outcome. Here is more or less the same, but the variables are not numerical, but it's actually, it looks more complicated, but it's even easier. If we change like the word, will the answer to these questions change? Well, no, actually not, because here we are asking if the group, which group is. Here we are asking the position, and here we are asking the group again. So the word is not really I mean, doesn't really change anything. So we will predict the same stuff if we, instead of using this one, we use Coppiaccio. And the prediction will always give me yes. So this is because I'm on the same leaf of the tree. So decision trees are really easy to compute, but mm, they, I mean, the problem is that they are too rigid, and you see, it's not really. It's easy to overfit them, so it is better to use random forests, which are, in contrast, very difficult to interpret. So let me also, I should conclude also the topic of uh, random of decision trees for numerical variables. So if y, what happens if y is numerical? Well, we have to change simply the impurity function, because those one were specifically done for a k-level factor, and two, we have to change the way of doing a prediction. Well, for the way of doing a prediction, we use the mean. So y we take for two, we take the mean of y in the group we have. For one, what is a measure of impurity? I mean, when is that y varies too much? So in that group, we want to predict using the mean. And when is that that the mean is not really informative and there are a lot of different numbers and they vary a lot. So say in group one, we want to predict y using the mean, but when is the mean really not informative? Let's say, what can be I mean, when is that the data closely clustered. So there is a lot of values, let's say, in the line, they're all concentrated or exactly. So if the variance is big, the mean is really doesn't tell you anything. So one can take as an impurity function the variance of y in the group. But for the rest, it's really the same. So This is simply for your knowledge, as I mean, as a course, university course could be. What else? So, a random forest, the last topic, which is quite okay. I need to. I mean, it's the idea is easy. So, is the following: we take many decision trees uh, as much independent as possible. What does it mean? This thing we will see it later. So many random decision trees, and we make them vote for the variable y, for the value of the variable y. So each tree has an prediction, and they all vote and say, okay, and the majority of trees will choose with the value of y. So the value of y will be determined by the majority by voting. So each tree will have a prediction for y, and the value of y can be chosen by majority, let's say, by voting. So the question is how these trees are defined. Random decision trees. Well, first of all, we would, if we had in the real world to make the decision trees independent and random, we would take one different sample per each tree. However, we cannot, because unfortunately, we are given with the sample we have. So we don't want to pay for another tree to do another one decision tree, and we can do like thousands of them. We would like to do. So we have to deal with this fact, and so what do? We do a bootstrapping sampling. Bootstrap. Do you know why? So the bootstraps are like the laces of the boots, and bootstrapping means so you can. It's like you try to lift yourself using your by lifting yourself from the bootstraps. So it's not, I mean, but in statistics works a little bit. So like we have, we take a sample from our sample. So how do we take it? In the following way, let me use a picture, it's better to. So here we have our data. Which is x1, xd, y. Which has like, say, m columns, m rows. And now we take a new sample from our data, which is, this is the bootstrap procedure. How? Well, we sample, we replacement from the columns, from the rows of the left. So like, for instance, for this column, also here there will be m rows. For this row, for instance, we choose this one. For this one, for instance, it happens that we choose this one. We do it randomly. Then it can happen that we choose twice the same row. And we will have something like this. So we will have a sample which is similar, but some rows are repeated and some rows are left out of the bag. So the rows of the original sample, which are not chosen. So this is important. We sample them with replacement. So let me write it better. So we sample from our sample. We take, if our original sample is from m observations, we sample with replacement m variables, m rows from the original sample. This is the bootstrap sample. And so what's the feature? It is, well, it is random because it is with replacement. And you see, there are some rows which are random, which are not chosen. So the sample is random. And these rows, because I don't know if it is really impossible to, if M is big, choosing randomly, to not choose twice the same row, because we are choosing n times. And if we choose twice the same row, there will be one row which is left out of the bag. So the rows of the original sample which are not chosen are said to be out of the bag. Well, that's a definition. Now with this data, with this bootstrap data, we build our decision tree. There is another, but there is another procedure that is also done, like it's a variable selection to make. I mean, is it clear what this bootstrap procedure is? I mean, we can do it like here. Like we go here and we define like a vector x equal to, I don't know, 2, 3, 4, 5. Okay. Well, this is a vector x. Now we can do we can sample from x with replace equal to how many variables? Well, the length of n of x. And so the size is so we sample a vector of the same size of x, but with replacement. So this is like a bootstrap data. You see, it is different, but for instance, the 52 here is not present. You can do it many times, and each time would be different. Um, so now it's more clear. Maybe it's not clear why. That's a good point, but at least the procedure of what I'm doing. Why is to try to make well, first of all, to make this decision trees random, because otherwise it would be always the same. Um, so let's wait 1 minute. Okay. Well, now we can. There is another layer of randomness that we add, and this like choosing the variable. Like each for each decision tree, we choose not all the variables, but only the ones we, not only a fixed, a determined random, so, but only like, I don't know, but a random subset of them. For instance, we could choose only group and position in the previous decision tree. Nothing would change. But if we choose like group and word, then the decision tree changes. If we neglect repetition. So this is another layer of randomness. After this, those two little like things to have in mind, this bootstrap and this variable selection, the algorithm is really building a lot of these decision trees. Simply decision trees and makes them vote. So let's see it in action. So the syntax is always similar. So let's use it for the same data set, which is Phono. So we can the syntax is always from the party library, and it is called cforest, the algorithm, the function. Well, the data is again phono, and we have to predict deletion using the group the position and the word. Then we have to pass other controls like okay, I need to recall the syntaxes. So yes, controls C4 standby is the syntaxes, sorry, simply. Uh, well, and I have to give, well, there is mtry. Okay, let me also look at the syntaxes of C4 standby. So mtry is the number of input variables randomly sampled, which was what I was telling about. So we don't take every variable, maybe we choose two of them, and let's choose two of them. So uh, mtry is equal to 2. So every decision tree will be made only with two variables chosen randomly. And let's take how many trees? Uh, let's take 40 trees. And and let's save it into my forest. Ah, that's it. I thought it would take more time. So, well, let's try to see. Ah, no, sorry, this is my forest. Okay, it cannot be plotted. Uh, but let me say my forest. Let's see. Maybe I can summarize. Summarize no, but summary yes. Okay, nothing special here, but we can use it to predict to give like let's try to see what are the prediction of my forest over my data set. Maybe I should. Okay, this should be like my predictions. So I mean, nothing you see now is much less interpretable. Everything you don't have your decision tree. It's only a bunch of yes or no. Uh, maybe you can see how each tree voted, but not even that. It's really difficult to interpret. But there is this stuff here, which is var imp of my forest, which gives you the importance of each variable. And now I will explain for the last thing of today how this importance is computed, because it's actually a nice idea if you never seen this. Actually, no, it's very smart. So here the word is the less important variable. In fact, so the group and the word itself doesn't is not important for deletion, it seems, or at least it, group and position are more important. Uh, how this function computes these these numbers? How does it make a classification? Well, this is nice because uh, uh, like overimp classifies, computes those numbers. So let's take one tree. So one tree from the forest. It is created using like C3 on the bootstrapped data, with maybe having removed some variables without and but it's not important for this discussion. So and after removing some variables. We want to see how the variable, how much the variable x1, for instance, x1 influences the prediction of of these three. Now, in linear regression, what do? Well, we remove one variable and we compute the new coefficients and we see whether the least square are better or, I mean, there was this multiple R squared, which was this measure. Now here, the tree itself is learned, is trained, let's say, using x1, xd. And we cannot remove it. Remove x1. Well, at least okay, at least we won't do that. So I'm not sure about this last sentence, but we have some prediction. Well, we would like to we would like to check if the prediction we would like to have some new data to train new data to check whether the prediction we would like to have some data done in such a way that one, some new data are is done in such a way that y is independent from x1 to some new data are independent, are real data, so they are sample data, not used to train to create the tree. So, do we have some data that we didn't use to create the tree? So we bootstrapped. We took a sample from the sample, and we trained the tree with that sample. Do we have we have those variables which are out of the bag? So we have those data. So we have some data that we didn't use for the tree. For instance, if we come back to the vector x and to sample from x, how was it? Sample. So for instance, here we have like we didn't see the 52. If we train something with this data, then we can use 52 and it will be it won't be spoiled the data. So for 2, we have the out of the bag data, which is left from the bootstrap method. We can check how good is the decision tree on that data. So is it clear? Like it's like we took some data, we make our decision tree, and then we have also other data that we know, and we can check whether the prevision given by the decision tree like agree or not. And this data, fortunately, is given by the bootstrap method because it leaves some data that we don't use. Then the problem is now how to create data where the dependence of y from x, 1, is neglected. So, for instance, and this is actually a very nice idea because what can we do? Well, we have this out-of-the-box data. Which is x1, xd, y. For instance, let's say that is 1, 3, 6, 8, some numbers here, 2, 6, 12, 16, 5, 2, 3, 1, 5, 5, 6, 6. And our decision tree gives me this prediction for y. For instance, I don't know. Sorry, let's take here some different numbers, 3, 4. And here it gives me the prediction like 2, 6, 12, 16. So more or less, it agrees on some numbers, the other one is different. Now, what do I do? Is it x1 significant? Well, we can test it. We can test the model on another data in which we shuffle x1. So we consider x1 tilde a random shuffle of it. So for instance, 8, 6, 1, 3. And the other columns are left unchanged. So 6, 5, 13, 5, 6, 5, 1, 2. And 3, 4, 12, 16. Now, what has this data? This is quite nice because now x1 tilde and y are independent since I shuffled them. So it's like, I don't know, I can do it here. So let's do the following code. So let's take x to be like 120, y to be the vector from 1 to 10, 20. So the plot would be the following. So they're clearly dependent. We can check also the core test. The p-value is ridiculously small. But now we sample, we order X, so X tilde, X ordered is simply simply here I'm shuffling X. So you see X and X ordered have the same number of elements, the same elements, but they are shufflable. Now I can plot it, X ordered and Y, and they are independent, so you cannot see. I can also do a core test, and this won't give me that they are. It will give me that the correlation is not significant. Okay, X ordered. So yes, the p-value is 0.6. They are not, because actually they are not independent. They are not dependent. They are uncorrelated. So I can do the same stuff here. I defined this new data. I apply again my decision tree, and it will give me something like 2 times the first column, so like 16, 12, 2, 3, which are completely different from the y's I had here. So this would be my predicted y. And so I can tell that the x1 variable is important. This is how the idea of how this works. So I shuffle the variable of interest, I apply my decision tree, and I see if they change my predictions. Change. So, and then there is some computations involved for giving those numbers, but the idea is this one. So I don't know, it was not, I mean, it is, I mean, it's not complicated, but it's a lot of stuff. So I understand if the last part was not so, but I mean, if you have questions, I can ask. I can answer, sorry. Mhm. Okay, then that's it for today. Next lecture, I won't be here, so will be online. Uh, okay, anything else? Just uh, okay, goodbye from those following online. Uh, that's it.